Okay, welcome back. We have taken our star up the red giant branch. We've had a helium flash happen. We're now steadily burning helium in the core with still a hydrogen burning shell around it. The question now is what happens to the sun after it runs out of helium in the core? Now, the helium is a much faster burning um, element, meaning you don't get as much energy out of burning helium as you did out of burning hydrogen. So this stage of stellar evolution, while somewhat long-lived, longer than say any red giant branch phase where it was constantly moving really at some slow rate, the helium burning main sequence phase lasts a much shorter time than the hydrogen burning main sequence phase did. And when it does run out of helium, it will happen in very similar ways as running out of hydrogen did. It will happen at the very center first. That region will then, again, not have any energy source available to it, so it will shrink down. The helium burning shells on top of it will shrink on top of it, heat up, and you will begin fusing helium at a faster rate. The hydrogen burning shells on top of it will shrink down and heat up, and again, begin burning hydrogen at an even faster rate. And so you're now burning helium in a shell around an inert carbon core, and you're burning hydrogen still in a shell around your helium shell. The same sort of things happen. You have more energy being generated in the center of your star that pushes the outer parts of the star out even more than they did before. The total luminosity increases, and the surface temperature will again drop. It'll move back up and to the right on the HR diagram. This is what that looks like. It will be even larger than it was before. So way down at the center here, you've got an inert now carbon, maybe some oxygen there, 2 core. You've got helium burning in a shell around that, and you've got hydrogen burning in a shell around that. And now the outer part of the star is pushed out almost to the Earth's orbit. The radius is now approaching an astronomical unit. And if there was anything left on the Earth, it's certainly vaporized at this point and not much left. So this defines a general pattern of all of these things. You burned an element in the core, first hydrogen and then helium. You run out of that element in the core contracts, you burn that element in a shell, and if your star is massive and hot enough, it will eventually get hot enough to burn the next element in the core. Well, this is not what happens now for the sun. The sun is not massive enough to burn anything beyond helium. And so, what happens next? The sun's core never gets hot enough for the next stage of nuclear burning to occur. So the same sort of thing happens before, though. The Pauli exclusion principle kicks in, and you have a region in the center of the star where you have basically a constant temperature and density. You have a carbon-oxygen core, and you get these kinds of shell flashes. And what happens is the helium burning will become so fast and bright that it will expand and stop burning. And then as it contracts and contracts and contracts and contracts, again, eventually it will be hot enough that that region can burn again. And what happened? We had a helium flash in the core of the star before. We now can have these flashes occurring in the shell of a star, and these flashes can transmit so much energy into the outer parts of the star that the very outer parts of the star can actually get lost to space entirely. The bursts of energy can be pushed into space, and the outer parts of the star can lose gravitational connection to the core of the star itself. And eventually, as the star goes through a successive shell flashes, all of the outer parts of the star can be lost. And this sets up something that's called a planetary nebula. Planetary nebula is a terrible name for something. It has nothing to do at all with planets. But this is what one of them looks like, and you can kind of see why they might be called planetary nebula. They kind of look like planets through telescopes, and that's how these things are almost always named. What did it look like for the first person who looked at something like this through a telescope? Why does this look like a planet? Well, again, the distinction between stars and planets through a telescope is that stars always appear as points of light, and planets appear as circular disks. You can actually resolve them. You can actually see the surface, the disk of the planets themselves, because they're so close to us. Well, these planetary nebulae are not planets, but many of them do resemble planets in that you can see an exposed disk of material. What looks like a disk, what looks like a ring. And so we call them planetary nebulas. They have nothing to do with planets. This is the exposed, this is the end states of a star like the sun. You can see the outer parts of the star have been ejected out into space in one cataclysmic event. And you can even see at the center the exposed star, the exposed core of this star. Okay, you want to see some more pretty pictures of planetary nebula? Good, I'm glad you asked. Here are some more pretty pictures of planetary nebula. Again, they all look different. The colors are probably somewhat enhanced or exaggerated. But you can see all of these have a beautiful region of expelled gas that is glowing very brightly. Why is it glowing brightly? Because you can see at the center of all of these, there is a very hot, extraordinarily hot, dense thing that is emitting lots of energy that is causing this gas to glow very brightly. And so you get these very nice, beautiful things to look at through telescopes. So what's left behind? We've got the core. Basically, the only thing that's left behind is the core. The only thing that's left behind is the carbon thing that is inert and no longer burning anything, no longer having nuclear fusion going on. Everything else gets lost into space. Gets not in an explosion, but just in a pushed away off into space kind of thing. It's extraordinarily hot, right? The surface temperature of this thing is like 100,000 Kelvin. It's the exposed core of this star. It's extraordinarily small. This circle with a plus inside of it is the Earth. The radius of these things are something like the size of the Earth, and they're extraordinarily dense, something like 10 to the 9 or 1 billion kilograms per cubic meter. We'll talk more about what that means in a bit, but this is an extraordinarily large number. What do we call these things? Well, they're very low luminosity because they're so small. They're extremely hot. We actually had a name for the things that were very hot on our HR diagram to the left and very low luminosity at the bottom of our HR diagram. We call these things white dwarfs. So the central region of all these things, the thing that's exposed and left over, is a white dwarf. And this thing is no longer a star. The star has to have some fusion going on in the center of it. There's no fusion going on anymore. We'll talk more about these things in the next chapters. But let's see some more pretty pictures of planetary nebula, because there are huge numbers of them, and they're all very interesting and beautiful and pretty. Here are some examples. Again, many of these you can see multiple epochs of material having been ejected at various stages. They all look a little bit different. They're all unique. It's pretty amazing. This is the Dumbbell Nebula. This is the Eskimo Nebula. I think this is the Ghost Nebula. Again, some of them have very circular structures. Some of them have multiple rings. Some of them have seemingly preferred axes that this material is getting ejected along. Some of them seem to have no axis at all. It's just a hodgepodge of things being ejected. The details, again, obviously are very complicated in how this actually happens. They're not even all circular. Some of them have very non-circular appearances. It almost looks as if the material that's being ejected is being nozzled in two directions. You can almost imagine in this lower right one, you've got the garden hose out in the backyard on very low power, and you are just seeing this all get nozzled around some central thing. What causes this nozzling? I'm not sure we know. It could be that these things are spinning really fast. It could be magnetic fields. And it's something that gives us some axisymmetric axis, some dipole axis, from which this material actually will get ejected. We'll do that. Okay, so to summarize, here we have the life track of a sun-like star from the main sequence through planetary nebula to white dwarf. this is the summary slide that gives you everything you need. The sun is a main sequence star. Will eventually run out of hydrogen and start to move up the red giant branch. This is what it will look like then. It has an inert helium core and a hydrogen burning shell until it reaches the tip of the red giant branch, at which time the helium flash happens and it moves down here. This is a helium burning in the core star now. We call this the horizontal branch. Eventually it run out of helium in the core and then move back up. This is actually called the asymptotic giant branch because it's asymptotic to the, if you like your math terms, to the red giant branch. And there you have an inert carbon core with a helium burning shell. That helium shell goes through these shell flashes, and you've got helium burning shell and a hydrogen burning shell. Eventually those shell flashes will eject all of the outer parts of the star. And this is dashed because this is sort of an instantaneous process. As soon as you can see the white dwarf at the center, it begins its life here. So it almost goes instantaneously from being a star that looks like this to, as soon as you're talking about the white dwarf being exposed, immediately down here to way below the main sequence. An extraordinarily hot object that is very low luminosity because it's so freaking small. That's it, the life track of a low mass star. Okay, and we will come back next time, meaning Thursday's class, and talk about what these white dwarfs are and how they're interesting, and also the life history of a high mass star. So stay tuned for that.